This video will cover section 9.3, geometric sequences and series. The objectives will be to recognize, write, and find the nth term of a geometric sequence. I want to remind you that last section was about arithmetic sequences. This is geometric, and we will find out how to recognize them and what makes them a geometric sequence. Also, how to find the sum or the addition of a finite geometric sequence. Remember, finite, it does have we know the last term. And this could be actually a partial sum of an infinite sequence. We could find a partial sum, like the word says that. Also, to find the sum of an infinite geometric sequence, this is not possible with arithmetic sequences. And if they're infinite, then the sum is infinite. With geometric sequences, there are some where we could actually find the sum of that infinite geometric sequence. I know it sounds a little weird, but we will learn how to do that. And then to use geometric sequences to model and solve real-life problems. We have learned that a sequence whose consecutive terms have a common difference is an arithmetic sequence. So to refresh your mind on that, those were, for example, the set of even numbers, for example, 2 and then 4, and or even integers 6, 8, and so on. So because the common difference between every two terms, 4 minus 2 is 2, 6 minus 4 is also 2, and so you could see that the common difference is a 2 because you could get the next term by just simply adding 2. And we learn how to find the nth term by using this formula, a sub 1 plus the common difference times n minus 1 times. Now, this was section 9.2. For this section 9.3, you will study another important type of sequence, and this is called geometric sequence. And I want to also point out that both of them are important in calculus, and you will learn more properties of them when you take Cal 2. Also, if you get to take differential equations, they will also be there. So consecutive terms of a geometric sequence have a common ratio. So for example, if I say I'm going to start with the number 1 and I want the next number to be that 1 times 3. So it will be 1 and then 3. My next term, I want it to be the previous term multiplied by 3. So that will give me 9. And my next term multiplied by 3, it will give me 27, and so on. So here, the common ratio, it's going to be the number that we multiply the first term by. So for example, it was a sub 1 times 3. And then we got that 3. Then for the next term, we took a sub 2 times 3, and that's how we got the third term, which was 9. And then after that, we took that third term and multiplied it by 3, and that is how we got the 27. So in this case, the common ratio, and we will use R for ratio, is going to be 3. How will we find this if we have a list of a sequence, a geometric sequence? Well, we will take the second term, a sub 2, and divided by the first term, a sub 1. So in this case, it could be 3 divided by 1, which is 3. Similarly, we could take the third term and divide it by the second term. So this will be 9 divided by 3, which is 3. So I'm only going to check 2, but yes, that gives us the same. That's why we call it common ratio. So here we have the definition of geometric sequence. A sequence is geometric when the ratios of consecutive terms are the same. Remember, consecutive, the one right after. And so the sequence, a sub 1, a sub 2, a sub 3, a sub 4, and then here remember the three dots represent, we don't know how many terms are in between. Sorry about my dog barking. And then we have a sub n as the last one. But the three dots here are indicating that the sequence could keep going. So in this case, it could be an infinite sequence. But remember, we have both finite and infinite. So this is a geometric sequence when there is a number r, which we found on the previous example that I gave you. It was r equals 3. So a sub 2 divided by a sub 1, like we did, a sub 3 divided by a sub 2. And that is true for every two consecutive terms. So all of them, if it is true that it's a geometric sequence, all of them should give you a ratio of a common ratio, which we use the letter R. And of course, that common ratio cannot be 0 because if that was the case, then all of your terms will be 0. And if you divide one by the other one, then it wouldn't work because we cannot divide by 0. So the number r is common ratio, and a geometric sequence may be thought of an exponential function whose domain is the set of natural numbers. And yeah, actually it is, because you are multiplying everything by the same number. So for example, the one that I gave you here, the 1, 3, 9, and 27, it also happens to be 3, an exponential function, if the base was 3. So 3 to the first power, that's a sub 1. Then a sub 2 is 3 to the second power. In fact, I'm sorry, a sub 1 is 3 to the 0 power. And that's how we get the first term, 1. Then a sub 2, remember this is how we got a sub 2, is 3 to the first power. A sub 3, it happens to be 3 squared, which is 9. And then a sub 4, it happens to be 3 to the third power. So if we were to find the next term, this will be 3 to the fourth power, which is 81. And so that's how we can compare a geometric sequence to an exponential function. But instead, for an exponential function, the domain is all real numbers. And in the case of sequences, the domain is only the set of integers, or in this case, natural numbers. So natural numbers, they start at 1, 2, 3. So I guess you can call them also the positive integers. Also, when we say natural numbers, we don't include 0. So based on the example that we looked at, I'm going to write it here again, where a sub 1 was equal to 3 to the power 0. A sub 2, oops, that's not A. A sub 2 was 3 to the power 1. A sub 3 was 3 squared, and so on. So you could see the relationship between the subscripts and the exponent. So you could see that the exponent is always going to be 1 less than the subscript. And so for that reason, you could see here in general terms, so to find the nth term, that n indicates the term that you have or that you're looking for. And so it's always going to be the first term, a sub 1, times the common ratio, and the exponent for that common ratio is going to be 1 less than the subscript, just like we've seen on those examples. So that's why we have n minus 1. And here we have a nice graphic of how a sub 1 is just a sub 1, then a sub 2 is a sub 1 times the common ratio. And then for the a sub 3, we could look at it as being a sub 2 times the common ratio. But if we already know that a sub 2 is equal to a sub 1 times r, then I can substitute that here, and that will replace a sub 2. So if I write the other r right there, you could see that we will get a sub 1, and we have r multiplying by r, so that makes it r squared. So once again, we could see how if the subscript is a 3, we're actually multiplying the first term times the common ratio to the power of 2, 1 less than 3 than the subscript. So when you know the nth term of a geometric sequence, you can find the nth plus 1 term, meaning let's assume n is representing 9, the 9th term. So to find the very next one, which will be the 10th term, that's what we're using n plus 1 just to generalize that it will be the right after one consecutively. So we could just take that and multiply one more time by r. So for example, if we have a sub 4, let's say, and I'm just going to use the same idea that we have here, a sub 1 times r, and actually it should be this one, 1 less than the subscript, so r to the 3rd power. So if the question is what is a sub 5, the term right after a sub 4, or the 5th term in this case, then we could take the term that we used previously, the a sub 1 r to the 3rd power, and then just multiply by another r. And so just like we've seen before, this will give us a sub 1 and then r to the power 4. And again, we have subscript of 5. Our exponent for the common ratio is a 4. So this is our first example 4, and wow, okay, so I guess not the first. So find the 12th term of this geometric sequence. So what do we need first? Well, we need to find what is the common ratio. How are we going to find that? Well, we can take the second term and divide it by the first, and that will give me 3. Let's try again with the third term, 45, divided by the second term, 15. And yes, that is correct. So we could say that the radius is equal, the common ratio is equal to 4. Not radius, ratio. Okay. Now, after we've done that, we're going to use the formula that we were using, that we saw on the previous slide. So to find the nth term of a geometric sequence, you will take the first term and then multiply by the common ratio 1 less than the subscript. So in this case, we need the 12th term. So we're going to need a sub 1 times r to the power 11, because that will be one integer less than 12. So I'm going to substitute what I have. So for the first term, a sub 1, that is here given to us in the sequence, so that is equal to 5. And then for the common ratio, R is going to be here where we found 3. I don't know why I wrote down 4 here, but that is very wrong. It should be 3. So we put the 3 here. So that will be times 3 to the power 11. And you could also see that here, the substitution. So we have the 5 times 3 to the power 11. And make sure that you follow the order of operations. So do not multiply 5 times 3. That will be very wrong, because first you need to take care of the exponents.